Hey, welcome back. It's time for the honors video example for chapter 1.2. So this is really chapter 1, section 2. Okay, that's what I mean when I say, a number, point, a number. 1 is the chapter, and what comes after the decimal is the section. Too easy. All right, so let's look at this. Let's look at some terms first. All right, telescope. It's an instrument that gathers electromagnetic radiation, or light, from objects in space, and it concentrates it for a better observation. So it takes that light, brings it in, and focuses it, and gives you a better picture because it also magnifies the picture so you can see it. It's like it's right there in your face. Now, there are a couple of different kinds of telescopes. There are refracting telescopes, and they use lenses to gather the light and to focus it. Whereas a reflecting telescope uses curved mirrors. So instead of the light going through something to give you a picture, this takes it and bounces it off and then focuses it for you to see. And we're going to find out that these are like the better ones, the better picture. But refracting telescopes are more common because they're cheaper. Focal point, because we said that that's where, that the telescopes are gathering the light and focusing it. It's a focal point that it's being focused on. And that's where the rays of light pass through a lens or that are reflected from a mirror converge. Okay, so where the lens and the light meet, or the mirror and the light meet, that's the focal point. There are two lenses. One is the objective lens, and that's usually the big one if you're looking at a telescope this way. That's the one that the light's coming in. And then the other lens is, an optical lens. It's the eyepiece one. It's the one that actually is magnifying the picture for you. Now, there are optical telescopes, which is what the reflective and the refracting are. They are optical telescopes. Those are the ones that are most common, and they're used to study visible light from objects in the universe. Okay, and we're going to talk about the difference between visible and invisible. Yes, there is invisible. Okay, and I'm watching my numbering now, so I'm not going to have a mistake and do that. So that was 1, and now we're on 2. And we've got a couple more terms up here. We've got electromagnetic spectrum. What's that? It's all the wavelengths of electromagnetic radiation. Okay, so it's light, and X-rays, and gamma rays, and microwaves, and all that stuff. And we're going to look at that. And there's also a non-optical telescope. I told you optical telescopes use the visible light. Well, there are things that are invisible to like the human eye. But we've created non-optical telescopes which make that invisible visible to our eyes. And so that's used to study the invisible stuff, the radio waves and infrared and all that stuff. So it's pretty cool. Now, some information of importance. The lens in the eyepiece actually magnifies the picture. I already said that. And because reflecting telescopes bounce the light off of mirrors, the picture you get is much clearer than a refracting telescope. Because remember, refracting telescopes are using a lens, and the light is going through the lens. Whenever something goes through, like the light coming down and it goes through our atmosphere, it's diffused, it's changed a bit, it's bent. Yes, you can bend light. That's what a refracting telescope is doing. It's bending the light, and so it actually makes the picture not as clear. It's not a crisp, clear picture. Earth's atmosphere, let's just go on. Earth's atmosphere can interfere with optical telescope observations. Also with non-optical, but we don't really use non-optical on the planet because you don't get as much. Anyway, the atmosphere really messes with everything. So we started putting them in space. And the one that everybody really knows about is the Hubble Space Telescope. Yeah. And I think I told you in class, plus we read it in the book, that, you know, there was a big oops. They ground that just a little bit too much, and they had to send up a crew later with kind of like a contact lens to fix it. And then we have refracting telescopes. Again, I said that it's made with a lens, so it's glass. Because the reflecting telescopes is bouncing the image off a mirror, it doesn't matter how big it gets, because it's still a thin mirror and it's being bounced off of. With the refracting telescopes, they can only get so big because you're making a lens out of glass, and at some point it gets too heavy. Not too heavy for you to hold up, because you can always put that on a stand, but it is too heavy for itself. It starts to, you know, sag. Have you ever seen a bookshelf and you keep putting weight on it, and eventually it kind of does this, and it's, you know, you've got like a curve? That's what happens with the lens. It starts to sag. When it does that, it distorts the picture. Now you really, you know, everything's all blurry and just not clear at all. So you can't have a big ginormous refracting telescope. That's how we invented the reflecting telescopes and went, hey, this is so much better. So that is why refracting telescopes are not used like tons. All right, now let's look at 1852. James Clerk Maxwell. He proved that visible light is only part of a greater spectrum of electromagnetic energy. Okay, so human eyes can see light from red to blue. Red to blue. You should know by now, red, orange, yellow, green, blue, indigo, violet. Okay, those are all the red to blue spectrum. We can see those colors. We can see that light. Red light, orange light, yellow. We can see that. All the other stuff we can't see. Our eyeballs just can't process it. So we can see the visible light, but James Clerk said there is so much more out there that we can't see. It's amazing. Okay? And we also know that light travels in waves. Okay? Like the waves in an ocean. Okay? Light travels in waves. Sound travels in waves. Everything's in waves. Hello? So red waves are longer. You know, they're farther apart between their up and their down. And then when you get to blue, they're like just, you know, very close together. Okay? So what's happening is basically if it's slower than red or faster than blue, we can't see it. We already know that Earth's atmosphere blocks most of the invisible spectrum. We're happy for that. Okay, ultraviolet, the UV rays, we don't like those to come in because it damages our skin. Okay, gamma rays, we'd all be like the Incredible Hulk. And, you know, microwaves, we don't want to be cooked from the inside out. You know, that kind of thing. So the atmosphere blocks most of that stuff, which is pretty much why we don't use non-optical telescopes here on Earth. Radio telescopes, they find radio waves. Okay, now those are about 1 million times longer than the red optical. We said we can see red. That's the longest one that we can see. Okay, radio telescopes are 1 million times longer. There's no way we'd ever see that. It's, oh my goodness, so long. Okay, the telescopes can actually be linked together. The ones that do radio telescopes, they can be linked together and you get a more detailed image of those radio waves. It's way cool. And you've probably never heard of this, but Chandra X-ray Observatory is a space-based telescope, and it detects X-rays. X-ray telescopes in space are sensitive. Okay? They can see things so clearly and at such a distance that, for instance, if you put something about the size of a frisbee on the sun, on its surface, besides the fact that it would melt, and you would die before you got it there. But if there was something on the sun that was the size of a frisbee, the X-ray telescopes could see that. That's a big, long distance. And we're going to talk about that when we look at just how big is our solar system. So keep that in mind. It can see a frisbee that far away. It's amazing. Okay, so that's 3. Now, ta-da! Assessment 4. And I am going to change it to J, so just so you know. So assessment. What limits the size and magnification of a refracting telescope? Number 2. What is the advantage of linking radio telescopes? Why would we want to do that? And then list the types of radiation in the electromagnetic spectrum from the largest wavelength to the shortest. And I think I deleted this part. So don't worry about that. I just want you to give me this stuff. Give it to me, boop, boop, ba-doop, in order. That means you're going to have to look in your textbook because I did not cover that in this lecture. But it is in your textbook, so please go look. We already know that, the visible light is in there, but there's stuff before it and there's stuff after it. So put them in order. So go to Jupiter, do that. I will see you in class. Return to me with joy and honor.